Let's go over some examples of function transformations. The function on the picture is the parent function, so the x squared is shown on the picture in red. The minus 4 is kind of outside of the square, it's just tacked onto the end, so that makes it a vertical. Minus 4 means that it's a shift that'll move down 4. And really all that's going to do is affect the y value. So each y value, like this y value up at 4, minus 4 is 0. Y value up at 1, minus 4 is negative 3. The x values stay the same, it's just the y values that are affected. And that's why it's a vertical shift. Here we have another function where the 3 is on the outside of the parent function, on the outside of the absolute value. It's multiplied this time. Since it's on the outside, it's vertical. Since it's multiplied, it's going to be a stretch by a factor of 3. What that means is that each of these points, for example, this point that's up at 2, 2 times 3 is 6. So again, we're just doing vertical, only affecting the y values. This is up at 1 times 3 is 3. But it's a times. So this point that's up at 3 times 3 would be up at 9. You can see why it's called a vertical stretch, because anything above the x-axis gets stretched up. If it were negative, it would get stretched down. Vertical stretch. Here's another example where this negative sign is outside of the parent function, outside of the square root, which means it's a vertical. In this case, a reflection, anytime you see the negative sign. A vertical reflection is just a fancy way of saying over the x-axis. So each of these y values, again vertical y values, is going to be the opposite of what it was. 0 stays at 0, and it just flips over the axis. This one is the first one where the plus 3 is actually on the inside of the function. Our parent function is 1 over x. If it were like this, that would be a vertical and up 3, but since that's grouped in with the x value, it's kind of inside of the function, then we know it's going to be a horizontal. In this case, a translation 3 to the left. Now why is it left? Well, we know it's always opposite, but think about it this way. On the original function, x equals 0 doesn't work very well, and that's why we had a vertical asymptote. On this function, x equals negative 3 has that same effect. So x equals negative 3 will not work and becomes our vertical asymptote. What that means is that for each of these values, a 1, when we plug in a negative 2, it has the same effect as when we used to plug in a 1. So basically, each x value moved 3 to the left is going to have that same y value pop up. So it's almost like you can think of it as what kind of x values do you need to plug in that will cancel out that plus 3. And that just means we're going to be 3 to the left. Here's another one. Can you tell whether this 2 is inside the function or outside? The parentheses kind of give it away. It's inside, which makes it horizontal. Just like a horizontal shift left says plus 3, a horizontal shrink, these always are kind of opposite, right? It's going to be a shrink by a factor of 1/2. Again, because it's horizontal, we have to think about shrinking to cancel out that times 2. So each of these, now we're on x values, right? Each of these x values will be cut in half. This one's out at 2, it will be cut in half. Cut in half, cut in half. The 0 cut in half is still 0. And so it just got squeezed in horizontally. Had this been a fraction, like let's say 1/3, then that would have been a horizontal stretch times 3, and then it would have widened that thing out. This negative sign is inside the square root, so it's a horizontal reflection. Horizontal meaning over the y-axis, so values that were positive become negative. If there were any that were negative, they become positive. reflection. We have some compound transformations now. First, I'm just going to put on the parent function. We'll use red, x cubed. And so these are those graphs that we can graph in 5 seconds or less. And I'm not even going to connect them because I just want to think about those points. So 2 cubed, 1 cubed, 0 cubed. That's how I'm getting those points. And neither of those, the negative nor the 1/4, are being cubed. They're sort of just sitting out in front of this x cubed. And that means that we've got two vertical transformations going on. We've got a vertical reflection and we've got a vertical shrink by a factor of 1/4. And so if you're good enough, we could try doing these both at the same time. So for example, this point that was up at 8, again, I'm thinking only vertical. Up at 8, I need to reflect that. It would be down at -8. And what is -8 shrunk by 1/4? Times 1/4 would be -2. So again, I'm just going to take each y value, I'm going to reflect it over, and then quarter it. 0 doesn't get reflected anywhere, and when you multiply by 1/4, it's still 0. Now, points that were down below get reflected up, and then multiplied by 1/4. This one will be easier to see. The one down at -8 flips up to +8, multiplied by 1/4 is 2. And so this just kind of looks a little squattier than the old parent function, right? Maybe I should draw in the parent function. The parent function was super stretched out like this. But this was a vertical shrink, so everything got sort of compressed into that x-axis. All right, here comes our order of operations. We've got this vertical reflection. It's outside of the absolute value bars. And then I'll probably just do these both at the same time. A +2 is going to go left 2. -3 is down 3. So first I'll want to think about reflecting. Let me get a few points on there. The absolute value graph, do we know it? Alright, so first we're going to want to reflect vertically. So for example, this point right here is now going to be down here. Maybe I will just reflect those first. Upside down V. And then everything's just going to get moved. Left 2, down 3. Left 2, down 3. Kind of like our new vertex there, right? Left 2, down 3. But you have to do your reflections and your stretches and shrinks first before you can be moving left, right, up, or down. This last one is kind of a big deal. We talked about this, how if you have more than one thing going on inside a function, it's better to have it written in factored form. That's going to give us a true idea of our left-right movement. So here we've got this inside the function reflection. So it's a horizontal reflection. And our other horizontal is that what turns out to be a +2, which means it's left 2. You wouldn't have noticed that had we not factored. You would have thought it was right. So that's why factoring under there is so important. Our parent function, graphed in 5 seconds or less. There it is. And I need to reflect, then move left. So reflecting, then moving left. Let's just see the reflection. Oops. There it is. And then I'm going to move all of that left by 2. Left 2, left 2, left 2, left 2. And that's it.